Hello everyone, welcome to my channel. If you are new to my channel, please subscribe to my YouTube channel, so you can join our tech family. If it is informative to you, please like our video, share it with your friends so they can get help with these video, and don't forget to press all notification bell icon so you get regular update and don't miss any single video.
Antivirus evasion. In an attempt to compromise a target machine, attackers often disable or otherwise bypass antivirus software installed on these systems. As penetration testers, we must understand and be able to mimic these techniques in order to demonstrate this potential threat. In this module, we'll discuss the purpose of antivirus software and outline how it's deployed in most companies. We'll examine various methods used to detect malicious software and explore some of the available tools that will allow us to bypass antivirus software on target machines. What is antivirus software? Antivirus is a type of application designed to prevent, detect, and remove malicious software. It was originally designed to simply remove computer viruses. However, with the development of other types of malware, antivirus software now typically includes additional protections, such as firewalls, website scanners, and more. Methods of detecting malicious code. In order to demonstrate the effectiveness of various antivirus products, we'll start by scanning a popular Meterpreter payload. Using MSF Venom, we will generate a standard portable executable, or PE file, containing our payload. In this case, a simple TCP reverse shell saved as binary.exe. Next, we'll run a virus scan on this executable. Rather than installing a large number of antivirus applications on our local machine, we can upload our file to VirusTotal, which will scan it to determine the detection rate of various AV products. VirusTotal is convenient, but it generates a hash for each unique submission that is then shared with all participating AV vendors. As such, take care when submitting sensitive payloads, as the hash is essentially considered public from the time of first submission. Based on these results, we can see that many antivirus products detected our file as malicious. We'll transfer the file to our Windows client for later analysis. In our terminal, we set up a netcat listener to receive binary.exe from our Kali client. And then, with netcat, we send binary.exe to our Windows client. And binary.exe awaits analysis on our Windows desktop. Before diving into evasion techniques, we must first understand the techniques antivirus manufacturers use to detect malicious code. Detection methods. There are multiple methods that antivirus manufacturers use to detect malicious software. The most common methods used are signature-based detection, heuristic-based detection, and behavioral-based detection. Signature-based antivirus detection is mostly considered a blacklist technology. An antivirus signature is a continuous sequence of bytes within malware that uniquely identifies it. In other words, the file system is scanned for known malware signatures, and if any are detected, the offending files are quarantined. With correct tools, we can bypass signature-based detection by simply changing or obfuscating the contents of a known malicious file in order to break the identifying byte sequence. To address the pitfalls of signature-based detection, antivirus manufacturers introduced additional detection methods to improve the effectiveness of their products. Heuristic-based detection is a detection method that relies on various rules and algorithms to determine whether or not an action is considered malicious. This is often achieved by stepping through the instruction set of a binary file or by attempting to decompile and then analyze the source code. The idea is to look for various patterns and program calls, as opposed to simple byte sequences that are considered malicious. Alternatively, behavior-based detection dynamically analyzes the behavior of a binary file. This is often achieved by executing the file in question in an emulated environment, such as a virtual machine, and looking for behaviors or actions that are considered malicious. Since these techniques do not require a malware signature, they can be used to identify unknown malware or variations of known malware more effectively. It's worth noting that the majority of antivirus developers use a combination of these detection methods to achieve higher detection rates. Bypassing antivirus detection. Generally speaking, antivirus evasion falls into two broad categories: on disk and in memory. On-disk evasion focuses on modifying malicious files physically stored on disk in an attempt to evade AV detection. Given the maturity of AV file scanning, modern malware often attempts in-memory operation, avoiding the disk entirely. On-disk evasion. To begin our discussion of evasion, we'll first look at 4 techniques used to obfuscate files stored on a physical disk. One of the earliest ways of avoiding detection involved the use of packers. Packers generate an executable that is not only smaller, but is also functionally equivalent with a completely new binary structure. The resultant file has a new signature and as a result can effectively bypass older and more simplistic AV scanners. Obfuscators reorganize and mutate code in a way that makes it more difficult to reverse engineer. This includes replacing instructions with semantically equivalent ones, inserting irrelevant instructions or dead code, splitting or reordering functions, and so on. Crypter software cryptographically alters executable code, adding a decrypting stub that restores the original code upon execution. This decryption happens in memory, leaving only the encrypted code on disk, all but invisible to signature detection. Encryption has become foundational in modern malware as one of the most effective AV evasion techniques. Highly effective antivirus evasion requires a combination of all of these techniques in addition to other advanced ones, including anti-reversing, anti-debugging, virtual machine emulation detection, and so on. In most cases, software protectors were designed for legitimate purposes, but can also be used to bypass AV detection. Most of these techniques may appear simple at a high level, but they're actually quite complex. Refer to your lab guide for more detailed information. In-memory evasion. In-memory injection, also known as PE injection, is a popular technique used to bypass antivirus products. Rather than obfuscating a malicious binary, creating new sections, or changing existing permissions, this technique instead focuses on the manipulation of volatile memory. One of the main benefits of this technique is that it does not write any files to disk, which is one of the main areas of focus for most antivirus products. Remote process memory injection attempts to inject the payload into another valid PE that is not malicious. The most common method of doing this is by leveraging a set of Windows APIs. Once the memory has been allocated in the remote process, we can copy the malicious payload to the newly allocated memory. After the payload has been successfully copied, it's usually executed in memory in a separate thread using the Create Remote Thread API. Unlike regular DLL injection, which implies loading a malicious DLL from disk using the Load Library API, reflective DLL injection attempts to load a DLL stored by the attacker in the process memory. The main challenge of implementing this technique is that Load Library does not support loading a DLL from memory. Furthermore, the Windows operating system does not expose any APIs that can handle this. Attackers who choose to use this technique must write their own version of the API that does not rely on a disk-based DLL. When using process hollowing to bypass antivirus software, attackers first launch a non-malicious process in a suspended state. Once launched, the image of this process is removed from memory and replaced with a malicious executable image. Finally, the process is then resumed, and malicious code is executed instead of the legitimate process. Inline hooking involves modifying memory and introducing a hook, or instructions that redirect the code execution, into a function to point the execution flow to our malicious code. Upon executing our malicious code, the flow will return back to the modified function and resume execution, appearing as if only the original code had executed. AV evasion, practical example. Now that we have a general understanding of the detection techniques used in antivirus software and the relative bypass methods, we can turn our focus to a practical example. Finding a universal solution to bypass all antivirus products is difficult and time-consuming, if not impossible. Considering time limitations during a typical penetration test, it is far more efficient to target the specific antivirus product deployed in the client network. For the purposes of this module, we'll install Avira Free Antivirus version 15.0.34.23 on our Windows 10 client. The Avira installer can be found in the Tools Antivirus Evasion directory. We'll launch it and step through the installation process. Once installed, we can check the configuration by searching for Start Avira Antivirus in the Windows 10 search bar. Launching this application will display the Avira Control Center, where we can enable the real-time protection feature. As a first step, we should verify that the antivirus product is working as intended. We'll use the interpreter payload we generated earlier and attempt to execute it. In this case, we're presented with an error message indicating that the system cannot execute our file. Immediately afterwards, Avira displays a pop-up notification informing us that the file was flagged as malicious and was quarantined. Let's see if we can get this file past Avira. PowerShell in-memory injection. Depending on our target environment and how restricted it is, we might be able to bypass antivirus products with the help of PowerShell. A very powerful feature of PowerShell is its ability to interact with the Windows API. This allows us to implement the in-memory injection process in a PowerShell script. One of the main benefits of executing a script rather than a PE is the fact that it's difficult for antivirus manufacturers to determine if the script is malicious or not, as it's run inside an interpreter, and the script itself isn't executable code. Furthermore, even if the script is marked as malicious, it can easily be altered. Antivirus software will look at variable names, comments, and logic, all of which can be changed in a script without the need to recompile anything. This is a basic template script that performs in-memory injection. The script starts by importing virtual alloc and create thread from kernel32.dll, as well as memset from msvcrt.dll. These functions will allow us to allocate memory, create an execution thread, and write arbitrary data to the allocated memory, respectively. The script then allocates a block of memory using virtual alloc, takes each byte of the payload stored in the $SC byte array, and writes it to our newly allocated memory block using memset. As a final step, our in-memory written payload is executed in a separate thread using create thread. Missing from our script is the payload, which we can generate with MSF Venom. For consistency, we'll use the payload from the previous example. We'll rename the buff variable from MSF Venom to SC as required by the script and copy the resulting output into the final script. With our shell code included, our script is complete. We'll check our script in VirusTotal. According to the results of the VirusTotal scan, only 6 AV products detected our script. This is quite promising. Next, let's scan the file with Avira. First, we transfer our PowerShell script to our Windows client with Netcat. Nice. Our PowerShell script didn't trigger any warnings. Unfortunately, when we attempt to run our malicious script, we're presented with an error that references the execution policies of our system, which appear to prevent our script from running. This is because PowerShell execution policies are set on a per user rather than a per system basis. Let's attempt to view and change the policy for our current user. Please note that in this instance, we have chosen to change the policy rather than bypass it on a per script basis, which can be achieved by using the execution policy bypass flag for each script when it's run. We've successfully changed the policy for our current user to unrestricted. Before executing our script, we'll start a Meterpreter handler on our Kali attack machine to interact with our shell. This Metasploit command uses the -x option to set up the payload handler, remote host, listening host, and payload type all in one line. Now we'll try to launch the PowerShell script. The script executes without any problems, and we receive a Meterpreter shell on our attack machine. Excellent. We have effectively evaded Avira detection on our target. Note that mature organizations often implement various machine learning software in order to analyze the contents of scripts that are run. Depending on the configuration of these systems and what they consider to be harmful, scripts like the one used in this example may need to be altered or adapted for the target environment. Shelter. Shelter is a dynamic shellcode injection tool and one of the most popular free tools capable of bypassing antivirus software. It uses a number of novel and advanced techniques to essentially backdoor a valid and non-malicious executable file with a malicious shellcode payload. While the details of many of these techniques are beyond the scope of this module, Shelter essentially performs a thorough analysis of the target PE file and the execution flows. It then determines where it can inject our shellcode without relying on traditional injection techniques that are easily caught by AV engines. These include changing of PE file section permissions, creating new sections, and so on. Finally, Shelter attempts to use the existing PE's import address table entries to locate functions that will be used for the memory allocation, transfer, and execution of our payload. Let's attempt to bypass our current antivirus software using Shelter. First, we'll install Shelter in Kali using apt. When executed, Shelter presents a terminal with a new console running under Wine. Shelter can run in either auto or manual mode. In manual mode, it will launch the PE we want to use for injection and allow us to manipulate it on a more granular level. We can use this mode to highly customize the injection process in case the automatically selected options fail. For the purposes of this example, however, we'll run Shelter in auto mode by selecting A at the prompt. Next, we need to select a target PE. Shelter will analyze and alter the execution flow to inject and execute our payload. For this example, we'll use the 32-bit trial executable installer for the popular WinRAR utility as our target PE, which we'll obtain from the RAR Lab downloads page. We'll copy the installer to our home directory. Before analyzing and altering the original PE in any way, Shelter first creates a backup of the file. As soon as Shelter finds a suitable place to inject our payload, it will ask us if we want to enable stealth mode, which will attempt to restore the execution flow of the PE after our payload has been executed. We'll enable this, allowing the WinRAR installer to complete normally, which could reduce user suspicion. At this point, we're presented with the list of available payloads. These include popular selections such as Meterpreter, but Shelter also supports custom payloads. Note that in order to restore the execution flow through the stealth mode option, custom payloads need to terminate by exiting the current thread. Since Avira detected our previously generated Meterpreter PE, we'll use the same payload settings here to test Shelter's bypass capabilities. We'll choose to use a listed payload. And we'll select the Meterpreter Reverse TCP payload. After selecting the payload, we're presented with the default options from Metasploit, such as the reverse shell host and port. With all parameters set, Shelter will inject the payload into the WinRAR installer and attempt to reach the first instruction of the payload. The injection is verified, and we're ready to test the malicious PE. We'll configure a listener on our Kali machine to interact with the Meterpreter payload, and transfer our PE with Netcat. Next, we'll manually scan the PE with Avira. Since Shelter obfuscates both the payload as well as the payload decoder before injecting them into the PE, Avira's signature-based scan runs cleanly. Once we execute the file, we're presented with the default WinRAR installation window, and we can complete the installation without incident. Our handler session reveals a valid Meterpreter session, but the session appears to die after the installation completes. This makes sense because the installer execution has completed and the process has been terminated. In order to overcome this problem, we can set up an auto-run script to migrate our Meterpreter to a separate process immediately after session creation. Let's rerun the WinRAR setup. After the migration completes, the session will remain active even after the WinRAR installation process completes. Our payload will even run if the WinRAR installation is canceled. Wrapping up. In this module, we discuss the purpose of antivirus software and the most common methods used by vendors to detect malicious code. We briefly explained various antivirus bypass methods that involve different techniques of in-memory shellcode injection and demonstrated successful bypasses using both Shelter and PowerShell. Although we've successfully bypassed antivirus detection in both of our examples, we have barely scratched the surface on the topic of malware detection and evasion.
We hope you enjoyed the video and found value in the content. We value your feedback. If you have any questions or suggestions, feel free to post them in the comments section or contact us directly via our social platforms. Thanks for watching.